diving straight into the fundamental rules of how we actually measure reality. Think about it. The entire foundation of all physics relies on universally agreed upon parameters. Without them, well, the whole shebang just completely breaks down.
Picture this. A visitor from another planet lands right here on Earth, points to a wall and tells you it's exactly 8 glitches tall. So how would you know its height? You wouldn't. It'd be entirely meaningless. This perfectly illustrates why universal standards of measurement are absolutely critical. Without a shared system, our scientific communication, and honestly just basic human interaction, falls apart completely.
So here's our agenda. 1. The measurement problem. 2. Length, from kings to light. 3. Mass, the ultimate artifact. 4. Time and the atomic clock. 5. Scaling our universe. And 6. Putting it all together.
Let's start with Section 1. The measurement problem, why standards matter.
You know, for centuries, Newton's classical physics worked just fine for everyday life. But modern physics, that changed the game. When we started tracking objects moving near the speed of light, or dropping way down into the quantum level, these mind-bending realities demanded incredibly precise, universal standards that absolutely wouldn't change over time. The solution finally arrived in 1960 when an international committee established the SI system, or Système International. And what's truly elegant about this is how it boils the vast, crazy complexity of mechanics down to just 3 fundamental units: the meter for length, the kilogram for mass, and the second for time. Literally every other quantity in mechanics can be expressed using just these 3 basic building blocks.
Moving on to Section 2. Length, kings to light. Way back in the year 1120, the King of England actually decreed that a standard yard was the exact distance from the tip of his nose to the end of his outstretched arm, which meant every time a new king took the throne, the measurements just completely changed. To fix this, in 1799, the standard became the meter, defined as 1/10,000,000th of the distance from the equator to the North Pole. Better for sure, but still a localized Earth-based standard. Fast forward to 1960, and the meter was defined as the distance between 2 lines on a platinum iridium bar in France. But, as you can guess, modern science needed something way more reliable than a piece of metal that could subtly expand or contract depending on the temperature. So, in October 1983, the meter was radically redefined by a true universal constant. It's now exactly the distance traveled by light in a vacuum during a fraction of a second, specifically 1/299,792,458 of a second. Because the speed of light is the same everywhere in the entire universe, our definition of the meter is now universally valid. The extreme precision of that massive fraction is just staggering to think about.
Section 3. Mass, the ultimate artifact. For over a century, the fundamental unit of mass was uniquely defined by actual physical artifacts. A great example of this is the national standard kilogram number 20, famously housed under a double bell jar. Established in 1887, the universal standard was a very specific platinum iridium alloy cylinder kept in Sèvres, France. Accurate copies, like kilogram number 20, were kept locked in vaults, heavily protected to prevent even a speck of dust or a change in air pressure from altering their mass even slightly.
Section 4. Time, the atomic clock.
Okay, so before 1967, our standard of time was defined by the mean solar day, which is basically a fraction of the time it takes the Earth to rotate once on its axis. But again, think back to our alien friend from earlier. This definition is based entirely on the rotation of our one specific planet. The Earth actually wobbles, and its rotation slows down by tiny fractions over time. It just doesn't provide a reliable universal standard.
Enter the highly precise cesium-Fountain atomic clock. This represents an absolute leap in scientific history. Instead of relying on clumsy, wobbling planets, these clocks measure the incredibly stable, unfailing vibrations of atoms themselves. To put that precision into perspective, this specific type of clock will neither gain nor lose a single second in 20 million years. No way a planet can do that.
Thanks to this amazing technology, one single second is now officially defined as exactly 9,192,631,770 periods of vibration of radiation from the cesium-133 atom. It is precise, it's totally constant, and it is a fundamental property of the universe.
Which brings us to Section 5, scaling our universe, intuition and reason.
Now, physics has to account for a literally mind-boggling scale of reality.
We're talking about dropping from the mass of the observable universe at 10 to the 52nd power kilograms, down to Earth at roughly 10 to the 24th power kilograms, all the way down to a tiny housefly at 10 to the negative 5th kilograms, and finally, right down to an electron at 9.11 times 10 to the negative 31st kilograms. The visual shock of comparing these extremes really shows just how robust and versatile our SI system has to be.
And because this scale is so massive, generating an intuition about typical values is absolutely crucial. As the old saying goes, you've got to think about your end result and determine if it actually seems reasonable. If you're doing the math and your calculations tell you a housefly weighs 100 kilograms, well, you've definitely missed a decimal somewhere. Always ground your math in reality and ask yourself if the end result makes physical sense.
Section 6. Putting it all together, derived quantities. So length, mass, and time, they act as our fundamental puzzle pieces. When you start combining them mathematically, you create what are called derived quantities. For example, multiplying two lengths gives you area. Dividing a length by a time interval gives you speed. It is incredibly elegant how the vast, complex world of mechanics is built entirely from just these basic building blocks.
Take density, for instance, represented by the Greek letter rho. It's a really prime example of a derived quantity. It's defined as an object's mass per unit volume. And if we break that down into fundamental quantities, volume is really just 3 lengths multiplied together. So density is simply a ratio. Fundamental mass divided by a product of 3 fundamental lengths.
Contrasting a couple of metals shows how this builds right into our real world. Aluminum has a density of 2.7 times 10 to the third kilograms per cubic meter, but iron, it has a density of 7.86 times 10 to the third. Iron is much, much denser. Picture holding a 10-centimeter block of really light styrofoam in one hand and a 10-centimeter block of super dense lead in the other. Their volumes are absolutely identical, but their masses are wildly different, all because of density.
So let's leave off with a quick, practical thought experiment. Say you're in a machine shop. You have an aluminum part and an iron part, and both have the exact same mass. Which one is physically larger? Well, because iron packs a lot more mass into a tighter space, the aluminum part has to be significantly larger to reach the exact same weight. Understanding these fundamental rules, length, mass, and time, is truly your master key to unlocking the rest of the physical universe. Thanks for joining me on this explainer, and as always, keep questioning the world around you.